Hello everyone. Today we are going to start with the previous year question asked from the topic of operating system as well as the computer architecture. We have a pooling for the way which we are going to complete with the computer architecture, and most of you have suggested that we start dealing with the previous year questions and then discuss the topic around the questions. That is what like most of you have asked for. So we are here with the previous year question on this topic for the operating system. Videos are already been uploaded, like entire operating system has been covered in that. And like if you are new and you are watching it for the first time, then do subscribe my channel and then go to the playlist in this channel, Aayu Pathshala, and go to the playlist wherein the playlist is named as DCIO Tech 2025. And there are multiple videos related to exam preparation. Go and check out, and those videos might be useful for you. And then the notes of this as well as the previous would be available on the Telegram channel, which you can access on the URL t.me/apdcio2025. So this is where I have been uploading the notes, basically the notes that we discussed here in the during the video itself. So that will be uploaded on this Telegram channel. So without further waiting, let us start with the first question. And the first question is asked with respect to the USB flash drive. Which one of the following memories is used in USB flash drives, digital cameras, MP3 players, and SSDs? See, in like USB flash drive, and options are given as the flash memory. So straight away you can cancel out two options from here. One is the like XNOR flash memory and XOR flash memories, because these are like the combinational circuits. See, even if you do not know exactly, you can eliminate these two options. Why? Because see, we have heard about the like the sequential circuit. We have studied this in the like digital electronics, the video of which is also uploaded. The sequential circuit, we have seen that the basic memory element, that is the basic memory element is what? A latch, and further from latch we have flip-flops. So a latch we have like NAND latch and NOR latch. We have never like we never implement latch with XOR gate or XNOR gate or any other gate. For example, we only have the NAND and the NOR. So if the basic memory element are made up of NAND and NOR, that means that the XNOR and XOR are not would not be the answer. So out of NOR flash memory and NAND flash memory, one would be the correct answer, and here the correct answer is the NAND flash memory. Why the NOR flash memory? It is first of all expensive, and second is that it has high density. What do you mean by high density? In a smaller portion, you can store a large number of data. On the other hand, NAND flash memory are like cheaper and have comparatively lower density. Now see, so most of the flash drive, USBs and everything are using the NAND flash memory. But now since we are talking about the NAND flash memory, let us see what are the drawback of this. First drawback is that it is like having a relatively low density. What other could be the drawback? The other drawback is like, or we can say the limitation is like, number one is known as the erase before write rule. What is erase before write rule? That means you cannot overwrite a page directly. You must erase the whole block before rewriting. Understand? That means if you want to reuse a block, this is a memory space, and there may be certain blocks. This space may be divided into certain blocks. So if you want to, you have stored a data over here, and you want to reuse or restore the data. If all other blocks are full, then in that case, what you will do that you cannot rewrite over it. First, you have to erase this block, make it empty, and then you have to store data on it. So this is the erase before write rule, which is in the NAND flash memory. Second is that the finite, that is finite, FINITE, finite program and erase cycle. So the number of time that you can erase a particular block and write a data in it is finite. That is not unlimited. So at a particular, after like if you are storing a data, a large number of data, and so a large number of erasure, like you have to erase the data, then again write the data, and then again you are doing this for multiple number of time. That is, you are erasing the data and writing the data again. So this is known as basically programming and erasing cycle. So there is a finite number of time that you can do that. Okay, after that time, the device will wear out. So these are two limitations of the NAND flash memory. Number one is erase before write rule, and number two is finite program erase cycle. So SSD, that is the solid state drive, basically they need a smarter management. Smarter management. What is that? So the smarter management is done basically by using two techniques. One is called the garbage collection, and another is called the wear leveling. What is wear leveling and what is garbage collection? See, in garbage collection, what happens whenever you update a data, The data is updated in the new page. Memory is divided into different pages. And the old one is marked as invalid. Okay. The old one is marked as invalid. So as you go on writing new data and new data, the old data that you have written that is going to be marked as invalid. And like after some time, all those invalid data are going to be cleared, freeing up the spaces. What do you mean by the where labeling? In where labeling, see, in where labeling, we ensure that, see, if suppose this is the memory block, we ensure that each blocks, like you are writing a data over here, you want to erase this, you want to erase this block, okay, and again rewrite it. But all other blocks are not being utilized. So these blocks are fresh. No data is written in it, and neither the data is erased from it. But only from certain blocks the data is repeatedly written off and or erased. So flash, what does the flash memory, NAND flash memory limitation was? Finite program and erase cycles. So here, even if the remaining portion of the block is not utilized and it is fresh to be used, but since some blocks are utilized very heavily, so this block will wear out soon. And if these blocks are wear out soon, the entire memory means the memory space will no longer can be utilized because a certain block has wear out soon. So in wear leveling, what we do in wear leveling, we try like to uniform utilization of the blocks so that all the blocks are uniform, and this will ensure the lives would increase of the memory. Okay, so if you are using the blocks uniformly and judiciously, all the blocks are utilized, all the blocks are erased and rewritten. So this will increase the like cycle of the memory or the tenure for which the memory can be used. So there are two techniques. One is called the garbage collection, and another is called the well leveling. So if garbage collection is done, what does it ensure? It ensures that the memory does not memory does not first thing it ensures that memory does not fills up quickly because after some time it collects all the invalid pages and delete that, make that like put that into the garbage. So it frees up the spaces. So it ensures that the memory does not fill up quickly. The second thing is that it also provides longevity. It also gives longevity. Longevity means increase the lifespan. Also the wear leveling also do the same thing. So there are two techniques that can be used to overcome the drawback of the NAND flash memory. One is the garbage collection, another is the wear leveling. Just remember these two terms. So coming to question number two, like which one of the following technique is used when the processor detects an interrupt? It branches to an interrupt service routine whose job is to pool each I/O module to determine which module caused the interrupt. So here we have given the four options: multiple interrupt lines, software pooling, daisy chaining, and bus arbitration. See, what is daisy chaining and what is bus arbitration? First understand that. So bus arbitration means in a computer you have a memory. Sorry, you have a memory, internal memory. You have an external memory, which you can access through input output device, say a flash drive or something. Then in the middle, you have suppose a processor or a CPU, and you need to transfer the data between the memory or the input output device directly or through the CPU. Like the data transfer could take place like this from CPU to memory and vice versa, from CPU to input output device and vice versa, and directly between the CPU and input output device. But to transfer this, we have a single bus. Bus means you just can you can take it like there is that single path. So this path or this bus carry what? It carries data, also the address. Same. Same bus is utilized. So now there could be multiple input output device, multiple resource, which would demand for the data transfer between the memory or the CPU. Suppose this is I1 and this want to transfer the data directly to the memory or copy the data from memory to the like input output device I1. Or then there could be another device I2 which could want the for which a program is running and it wants some data from the like input device I2 to proceed further. So the CPU may directly require the data from I2. So each would try to utilize the bus. So now if two or more devices is trying to access the bus at the same time, there could be a conflict. And that is known as the bus arbitration. To resolve that conflict, we can have like the different techniques, whether the hardware based or the software based. So those technique, one among those technique is the daisy chaining. It has nothing to do with the interrupt. So daisy chaining is basically a priority based bus arbitration technique where we predefine the priority. Like it is a hardware solution where we predefine the priority of the different lines, and any input output device connected to this line will be assigned priority P1. So whenever a device at P1 wants the bus access, accordingly with the priority, the bus access would be given sequentially, first to P1, then to P2, then to P3, and so on. So a daisy chaining and the bus arbitration are basically the technique for the resolution of the bus arbitration. Now, let us understand what happens or how do an interrupt is entertained. See, when you receive, first understand what is an interrupt. Suppose this is a processor, okay? So there could be many input output device. For example, keyboard may be there. Let us take an example of keyboard. There could be flash drive also, or some other devices as well. So keyboard, there could be one way of knowing when the keyboard want to send a data so that we can display it to the output device, that is the monitor. There could be one possible way that the microprocessor keep on waiting for the data from the keyboard, and it like go and check, means it waits for the interrupt request IRQ. Okay, that means it goes and check whether this device or the device connected to this input of IO port wants to send some data or not. Then it goes to the next to check, again next to check, again next to check. So this way, the microprocessor means spend most of the time in checking whether the processor want to send, or sorry, the input output device want to send some data or not. So this technique is known as pooling. This technique is known as pooling, where the microprocessor keeps waiting and serially or sequentially it goes to each input output ports to check whether any input data is coming from that port or not. But what are the drawback? That the microprocessor is like wasting its time waiting for the data from the input output device. The other could be like the other technique could be that whichever input output device, let us say that these are I1, I2, I3. Whichever the device, there could be an interrupt line. Say this is an interrupt line. Whichever device want to attract the attention of the processor for anything, like they want to send the data or receive the data or whatever is the requirement, they may send a request and set high the interrupt line. Set high the interrupt line. So when this interrupt line is high, now the microprocessor does not need to check I1, I2, I3 sequentially as it does in the case of polling. It just need to check that whenever the interrupt line is high, that means there is some device which want to send me the data. Okay, so it will see which device want to send the data, and accordingly it will check whether it is maskable or not. Maskable or not. For example, processor is maskable means whether the request could be ignored or it could not be ignored. Like for high priority inputs, the request cannot be ignored. And even if the microprocessor is doing some important work, it will have to stop that work and have to attend the interrupt. So that is the difference. It will check that. Then what it will do, it will save the status of its current process, save the status of its current process, and then will go to attend the interrupt. So if the interrupt is vectored interrupt, that means along with the interrupt, it has predefined address where there is interrupt service routine is there. Interrupt service routine is basically the steps that the processor need to follow when interrupt is like entertained. So this is ISR, known as the ICR. So the processor already know what program is to be executed. After the execution of the interrupt service routine, its program jumps back to its like the previous functionality that it was, or previous process that it was executing, and resume with that process. So what it does, it basically, if the interrupt is vectored, it basically go to the address and execute the interrupt service routine. However, in case where like there are no interrupt service routine, that is the non-vectored interrupt, which is known as the non-vectored interrupt, where along with the interrupt, the processor does not know what to do. So in that case, the processor will exactly go to I1 and ask what it need to do. If I1, like the interrupt request was not raised by I1, it will go to I2, it will go to I3 one by one. And this is what is known as pooling that we have already seen. So in the question above, see, it says that it branches to the interrupt service routine, deducts an interrupt, it branches to an interrupt service routine, ISR, okay, and whose job is to pool each IO module to determine which module caused the interrupt. The ISR means the ISR job itself is to pool each IO module to determine which module caused the interrupt. So when the processor will execute, it will what it will do? It will do the software pooling. Okay, we have understood why daisy chaining is wrong, why bus arbitration is wrong. So software pool is the correct answer for this. So in question number 3, see, in question number 3 also, there are different types of scheduling. Scheduling, we have CPU scheduling, we have completed in the operating system where we have seen the functionality of the dispatcher and also the ready queue and the scheduler. So we're not going to do it here again, but simply you can see that like there is an IO scheduling, which is like in the option number S. And if you want to match this, the input output is only in option number 1. So even if you do not know the rest of the term, like long-term scheduling, middle-term scheduling, or short-term scheduling, And you can by logic also see that IO scheduling means the decision as to which process pending IO request shall be handled by an available IO device. This thing we have done in the processor when we have seen the like IO management. So if is like option one, for S we have one. So from that only we can go for option A is the correct option, for where only one option is having S is equal to 1. So now let's move to our next option, option number 4. Question number 4, sorry. In a question number 4 also, there is a terminology used as like different page replacement, page fault disregard, thrashing, and demand paging. These four terms are used. So let us read the question. Which one of the following condition occur when the processor spend most of the time swapping pages rather than executing the instruction? Swapping pages rather than executing the instruction. Now we have done this. This is the concept of virtual memory. And we have seen that whenever a program becomes a process and it starts its execution, so the processor, what it does, it brings some memory, some pages, and put it into the main memory in the RAM. And because whenever the program starts executing, it requires some memory, some data. So the processor pre-planned and put some pages in the like the main memory. Okay. So if the now as the program execute the memory, the data it wants, those memory blocks are already available in the RAM. But in case that page is not available, what will the processor do? It will go again to the like the secondary memory, say a drive or something. It will bring the data from there and then put it in the main memory. This is known as the like first of all when data is not present, this situation is known as page fault. And then when you bring the required page or required block from the secondary memory to the main memory, this technique is known as page replacement. So we have understood page replacement and we have understood page fault. So when this incidence occurs on a large scale, that is for each instruction that is the program is having, each time the processor is going to the main memory, the processor does not find the required pages in the main memory. So what it will do, each time it will go to the secondary memory and now it will load that page into the main memory. Again, it will go to the secondary memory, load the page into the main memory. So most of the time will be like of the processor is wasted in loading the page from the secondary memory to the main memory. And this is what known as thrashing. So correct answer would be thrashing. In the next question, it is asked with us which of the following actions are to be performed by a processor if one or both of the operands are present in the memory. See, instructions. What are the instruction? Instruction basically depends upon the architecture. Okay, what architecture we are using in a computer. So in the instruction there are two parts. One is called the operation code or the opcode. Another is the operand. So the opcode could be like broadly categorized as the control, such as we have the call, jump, return, or it could be arithmetic like add, subtract, or it could be like logic, for example, and or etc. And operands, like in the operands, we may have like the data, direct data, or registers, or address. Okay. So depending upon what do we have in the operands, the instruction format could be of four types. Four types of format. Four type would be like zero address. Then we could have one address instruction. Then we could have two address instruction. And we could have three address instruction. Okay. Zero address instruction means those type of architectures in which we are not using any operand. Zero basically indicates the number of operand. So in stack based architecture, this type of instruction are used in stack based architectures. In one address example are push, pop, etc. In one address like instruction format, what we have? We have like there will be only one operand, so it could be like add a. That means whatever is there in the A added with the content of the accumulator. In two address, there would be like two operand, like add R1 comma R2. So here what we are doing, we are adding the value of R1 and R2 and storing the result in R1, the first one. Okay. Then we have the three address. In the three address instruction format, we may have like add R1, R2, R3. So here what we are doing, we are adding up the value of R2 and R3 and storing it into R1. So these are the different types of instruction format, and this depends upon the type of architecture you are using. So there could be four types of instruction format. One is the zero address, one address, two address, three address, where 0, 1, 2, 3 represents how many operands you are using. Okay. Now, basically, there could be different addressing mode. So let us understand what is addressing mode. So what does addressing mode tell? Addressing mode. So addressing mode basically tells CPU how to find the operand or data, how to find the data. Okay, it tells the CPU how to find the data. For example, this add is the opcode, and then what operates you are using that defines the instruction format. What operand, how many operands you are using define the instruction format. But how the data is retrieved from operand, that defines the address mode. So there could be 7 address mode. Quickly, I will go through them. The one is that the immediate addressing mode. Immediate addressing mode. If you are interested, you can note it down. In immediate addressing mode, for example, we say that move R1, 5. The data is directly given. That means the value is the part of the instruction itself. Okay. So this 5 will be moved to R1. Then the second one is direct addressing mode. Direct addressing. The example could be like in the direct addressing mode, you give move R1, 5,000. This is nothing but this means that this is the memory location, a direct memory location, and whatever is stored in that location, whatever is stored in that memory location, you copy the content from that memory location and put it into R1. This is called direct addressing. Why direct addressing? That means the data that we are interested in is stored in a memory location, and the address is directly given. Okay. This was called the immediate because you do not have to access the memory over here. The data is immediately given. Don't have to go to the memory or to access the data. Number third is indirect. In indirect addressing, like instead of like move R1, instead of this 500, we are giving the indirect reference. That means you go to the memory location 500, sorry, 5,000, and there you have like another address. What the content is stored at 5,000 is not the data, but the address. Now at that address you go and you will find the data. That is here in indirect addressing, you are fetching twice. How many times you are fetching twice? First, you are going to 5,000 memory location. You are fetching the content in it, and that content is not the data. It is the address of the data. You go to that location and then you get the data. This is the indirect addressing. 4 is the register addressing. Register addressing. Suppose add R1, R2. See, the data is in itself is placed in the register. We have so many like the general purpose register with the CPU. So data is stored in the register only. It might happen that in some during the execution of some program, you want to temporarily store some data or the result in some register. So you use that like the general purpose register to store the data. So you can also want to use the data stored in that register. So you do that by direct register addressing. Okay. Now next we have the register and direct addressing. Register and direct addressing. Here, for example, the register will like if you want like you can say add R1, R2 will be written in small bracket. So this bracket indicates that R2 is not the data. It is basically holding the location where the data is. For example, if R2 is 5,000, it means that you have to go to the memory location 5,000 and then at that location data is there. You bring that data and add it to R1. Understand? So this is register indirect addressing. The other addressing could be like relative addressing. Relative addressing. So relative addressing is like very important. So effective address here, how do we calculate the effective address from where the data has to be like fetched? Effective address basically comes by combining the address that is in the program counter. What does the program counter hold? The program counter basically hold the address of the next instruction that is to be fetched plus offset. So this is the effective address in case of relative addressing. And the most common example of such type of addressing is used like in the controlled instruction. For example, jump plus 20. That means what? This is the offset value. The program counter, like suppose this is the number of programs and these are stored at 1, 2, 3, 4, 5 memory location. So now you are executing 3. You want to jump to 5 memory location. So you will give what? Program counter is holding what location? 4, because it holds the memory location of the next instruction that will be fetched. So it is holding 4 and you want to come to 6. So you will, what you will give? You will give jump plus 2. So it will, if effective address would be like PC plus 2 and PC is what? 4. So this is called the relative addressing. The last one is called the indexed addressing. Indexed addressing. And here the like effective addressing is given by effective address is given by base plus index register. Base plus index register. And this type of addressing is common when you are basically accessing the array. Okay. So these were the different types of addressing mode we have seen the instructions format. So now let us come to the question. So it's saying that performed by the processor if one or both of the operands are in memory. Both of the operands are in the memory. So in memory there could be like, so if these are in the memory, that means what? It can be like the direct addressing or it can be indirect addressing. It is not the immediate addressing, because in immediate addressing the direct value is given. So in that case, like either you can have like this add r1 comma 5000 direct addressing, or you may have address r1 comma 5000 in a bracket, that means indirect addressing. Both these cases are possible. So calculate the memory address based on the address mode. This is correct. We have seen that. If the address refers to a virtual memory, translate from virtual to the real memory. This is also correct. Determine where the address item is in the cache. Obviously, therefore we have like in computer architecture we have the memory hierarchy. I will discuss this also. Let us discuss this also. See, the memory hierarchy. First of all, we have the register. This is the fastest one. Then we have the cache. Then we have the main memory, which is also known as the RAM. Then we have the hard disk drive or the solid state disk drive, SSD or HDD, that is known as the secondary memory. So whenever the processor, microprocessor, want to access some memory, it will not directly go to the like SSD. It will follow the hierarchy. It will first see registers, then it will go to the cache, then it will go to the RAM, and then it will go to the SSD. 90% of 90 to 99% of the time, the memory, the data that is required is available in the cache, and if it is not available, it is made available. So the first of all, microprocessor will check the cache, and here it comes the like the cache replacement technique, which is based on the locality of reference. Locality of reference, where we talk about the spatial locality and temporal locality. So these two types of locality of reference are present. So in the cache, and then like if the data is not available in the cache, the data is fetched from the RAM, and then data is again put back into cache. So and on this we have the like the cache replacement techniques. That is the least recently used, most recently used, and then we have the first in first out technique. These are the cache replacement technique that we have. So we have seen these techniques are present there. So let me now discuss in brief what is the spatial locality and temporal locality. See, whenever the microprocessor wants to access some data and it is not available in the cache, so it has to be bringing from the main memory, and then there is high chances that suppose this is the main memory RAM, okay, and one data is present over here, and since the program is continuing in execution, there is high chances that the in the next instructions or in the coming instructions, the data from this part of the memory can also be fetched. So this is basically called the spatial locality. Called the spatial locality. That means the data from the nearby location can also be required by the processor. So what it will do, it will try to take all these blocks and put it into the cache. Okay. Now there could be three techniques: direct mapping, associative mapping, and set associative mapping. That is a different topic. We will deal it differently if required. So it will do like that. And what about the temporal locality? It means that if the data is used, if this data is used, suppose if this data is required at this time, it is high chances that this data may also be used at some time t greater than the t1. Suppose we are requiring this data at t1. So after some time we may require this data again. We means the processor for the for execution of the process. So this data will definitely be put into the cache based on the temporal locality. Also, the nearby data or the nearby memory blocks will also be put into the cache based on the spatial locality. So this is what it is done. So in the question, we are given one option as determine whether the address item is in cache. Yes, obviously. Calculate the data type based on the address mode. Yes, obviously. So all these four options are correct. The correct answer will be 1, 2, 3, 4. I hope you understand these points. So now let us move to the next question, in which, in the context of an instruction set, which of the following principle indicate that other elements of an instruction are independent of the opcode? Other element means what? The operand. We have the opcode and the operand. The operands are independent of the opcode. What is that? What could be that property? See, direct addressing and indirect addressing we have seen. And direct addressing and indirect addressing, it is no relation with the opcode. So, like opcode and operands are different, but it is asking that the elements of the instructions are independent of the opcode. Okay, so that property is basically the orthogonality. So, orthogonality, even in the signal system, we have seen that two signals S1T and S2T are independent of each other when their multiplication is resulted into zero. That means there are no relation in it. Also, we say that the autocorrelation function of or the cross correlation function of those two signals are zero. So, from that angle, also orthogonality will be the answer. Next question, which of the following bits indicate whether the instruction should be interpreted as a normal ARM instruction or thumb instruction? Okay. Before this, let us go to the question number 8 and then we will take up the question number 7. In the question number 8, it is asked which of the following techniques are used to maximize the instruction level parallelism. That means the multiple level of instructions or multiple instructions are executed or are processed parallelly. So the option 1 is the combination of compiler-based optimization and hardware techniques, the combination of computer-based optimization and software technique. See, parallelism is not a software-based technique; it always requires a hardware-based technique. So software means this is and this option does not suit. A combination of software-based optimization and hardware-based technique could be a possibility, and the combination of compiler-based optimization and hardware techniques could be also a possibility. But the most suitable answer is option number A. So let us go back to question number 7, where it is asking about the ARM instruction. So let us understand in detail what is an ARM instruction, because maybe question on this ARM instruction may come. See, I told you earlier also that instructions basically depend upon the type of architecture. So here in ARM architecture, we are actually having two types of instruction set. Okay, the original ARM architecture basically used the 32-bit instruction set, and these 32-bit instruction set were known as the ARM instruction set. ARM instruction set. But since they are using large number of bits, that is 32 bits, it is very expressive. Large number of instructions can be written. The drawback was memory consumption was high, and each time you do not require that basically there's such like lengthy instructions to execute some small work. So another version of the another instruction set came for the ARM architecture, and that was 16-bit. So 16-bit architecture means instruction sets were then made, and these 16-bit instruction set are known as the thumb instruction set. Why these were made? Just to overcome the limitation of high memory consumption even for the execution of small tasks. So now in the same ARM architecture, there are basically two type of instruction set. Number one is the ARM instruction set, which is of 32-bit, and number two is the thumb instruction set, which is of 16-bit. So how would like the processor know which instruction set or the given instruction belong to which instruction set, whether it is a 16-bit or 32-bit? There must be something which differentiate that. So that is what called the T-bit. So for example, in the question, it is asked that which bit indicates whether the instruction should be interpreted as normal ARM instruction or the thumb instruction. So the answer is T bit. So now let us see some detail on it. So basically, there is a current program status register CPSR, which is of 32 bits. So these 32 bits, one of the bit is T bit. Among these 32 bit, one of the bit is T bit. So there could be these bits, 32 bits can be categorized into three parts. One is called the mode bit, another could be the control bits, another could be the conditional flag bit. Conditional flag bits. Okay, these three bits, three categories of bit. So suppose this is the register of 32-bit. So this is the least significant bits, and this is the most significant bits. Okay. So the least significant bits, the mode bits basically we have from M0 to M4, and this is present at the least significant side. In the most significant side, the last bit is basically the N bit, which is indicated as N, and then we have the conditional flag bit. We will see what are these conditional flag bits. Okay. So, and in the middle we have the like control bits. So what are the different conditional flag bits, control bits, and mode bits? Let us see one by one. So conditional flag bits, we have like N, which is the MSB. Then we have the Z, C, V, and Q. So when N is basically means what? N is the negative flag. Negative flag. When N is 1, it means the result is negative. We have seen this in the previous digital electronics video where we have talked about the most significant bit. If it is 1, it indicates that the result is negative. So this is the negative flag bit. This is the zero flag bit. When this is 1, it indicates the result is 0. This is a carry flag bit. When this is 1, it indicates that there is a carry. This is overflow bit. And this is the saturation flag. Just remember the name. Saturation flag bit. Okay. Carry, overflow, negative flag, zero flag, carry flag, V for overflow flag, and saturation flag. So these were the the conditional flag bit. Then we have the control bits. Control bits would be remembered as IFATE, IFATE. Out of this T we have already seen. If T is 1, that means the instructions are thumb instruction. And if T is 0, it means it is the ARM instructions. Okay. What is I? I is basically known as the IRQ disable bit. IRQ disable. IRQ means the normal interrupt. When the interrupt is normal, this IRQ is made 0. If it is high, it will disable the normal interrupt. Then we have the fast interrupt, FIQ, fast interrupt. This is the fast interrupt disable bit. If you want the fast interrupt, so this bit has to be made 0 because when F is equal to 1, the fast interrupt is disabled. This is asynchronous abort bit. When you want to abort the instructions or the execution of the instructions, make this bit as 1. Asynchronous abort disable bit. So these are disable bit. If you made them high or 1, this will be disabled. This functionality will be disabled. So T we have seen this is asynchronous abort disable bit. So E is like, so again for E, let us understand that in ARM architecture, basically there are two memory format. One is called the little, just remember the name, Indian, starting from E, not I. And another is called as the big Indian, NDN. Okay. So for little Indian, if we want to use the memory format like little Indian, the value of E will be 0. For big Indian, the value of E will be 1. So basically to select the memory format, this bit is used to select the memory format. So we have seen I, F, A, T, A, I, F, A. Okay. So what are the mode bits? See, the processor like can operate in different modes. So what are the different modes that a processor can operate in? One is called the user mode, which is used for normal application. Okay. Then there would be FIQ, fast interrupt. Then there could be IRQ, that is normal interrupt. And we have seen that the processor could operate in FIQ and IRQ depending upon the control bit I and F. Then we have the supervisory supervisory role. Then we have the abort role or undefined role. So for normal application, the role of the processor is user. For other like operating system related operation, any of these roles would be used by the processor while executing the instruction depending upon what mode is given. Okay, like these will be having some code. For example, for undefined 1001 or something like that would be there. Accordingly, the processor will decide. So this is all with this computer architectures. We have holistically covered the previous year questions and the topic around it. Also, the comprehensive discussion on the each of the option has also been done. So this is all with this topic. Thank you.